participate in this wonderful session and to contribute to what I hope is going to be a nuanced discussion about scientific infrastructure and the representation and interconnection of knowledge. What we're doing today is speaking about space science, but the implications of this work span across fields. My hope is to provide a framework that spans fields and knowledge bases too, one that is capable of supporting the science we need in heliophysics in all domains now. The framework will be one of a knowledge commons. The commons is an important idea for conceptualizing many of the problems we face today with data, information, and digital spaces. In some ways, the challenge of our generation and those we are discussing across heliophysics now is to keep the pathways to discovery of future knowledge open and to support the flourishing of our communities and our science. First, I think we need to begin by understanding the challenge that confronts science today. Our world is increasingly interconnected. Making sense of the complexity is at the center of society's most grand, exigent, and obstinate science questions and requires systems-level understanding, or complexity science. Let me introduce briefly what I mean. What all went into the discovery and creation of the automobile? This is a complex object, meaning many parts had to come together for the automobile to emerge. Many domains and pieces of knowledge. We had to know about things like combustion, rotational dynamics, feedback control systems, and how all these pieces could interact for a given purpose. It's a remarkable interconnection of knowledge that produced the car. But once it was created, an entire ecosystem of things was made possible. The road, the suburb, speeding tickets, the traffic jam. I really love Isaac Asimov's quote that it would have been easy to predict the automobile in 1880. It would have been very difficult to predict a traffic problem. The former is really only an extrapolation of the railroad. The latter is something completely novel and unexpected. The motivation of this talk is that scientific discoveries are complex objects too, requiring the convergence and interconnection of many different things, different theories, data, the collaboration of individuals, and the innovation, the change that it leads to, but also about how we can create these interconnections and what is possible when we do. The realization has vital implications for our infrastructure, as I'll demonstrate. I want to relate scientific discoveries to the automobile, scientific discoveries that we hear about repeatedly. The ones our community most hopes to make are complex objects too, requiring the convergence and interconnection of many things, different theories, data, and collaboration of individuals and groups. What must come together must be interconnected to emerge the complex object that is something like the understanding of a star or when a star will flare. What must come to get together to emerge the complex object that is the understanding of the path and intensity of a hurricane. The realization is that these scientific discoveries require new things being brought together: facts, information, data, and individuals. Depending on the extent of integration of information required for a question that we're asking, there are different ways of doing that science. I would argue that our science questions are increasingly moving us into this upper right quadrant, the wicked problems regime, as we've called it, where we must converge many more information streams and make sense of them than we might have needed to in the past. As we broaden what we must consider in making new scientific discovery, we become overwhelmed in information. The challenge that raises was articulated by renowned systems thinker and computer scientist Herbert Simon. He spoke, "In an information-rich world, the wealth of information means a dearth of something else, a scarcity of whatever it is that information consumes. So a wealth of information creates a poverty of attention and a need to allocate that attention efficiently among the overabundance of information sources that might consume it." I think we all recognize this issue in our own scientific workflows. We are constantly asking questions such as, what papers should I read? What data sets are available and what are their relationships to one another? And who else has studied this phenomenon? What progress have they made? The implication for infrastructure is that we need to better direct attention and facilitate integration of information, search and discovery. Before I move on, one note about what I mean by infrastructure. I appreciate this session's broadening of that definition. It includes stored data, search and discovery tools, computational resources, analysis tools, not merely crunching the numbers, but scientifically informed analysis, as well as visualization and interactivity. In responding to these challenges, it is important to keep in mind this capacious definition of infrastructure. So what are these implications and how are we responding to them? Our response has been to create something that we've been calling the Heliophysics KNOWledge Network. And this is in partnership with projects that we've been leading through the Heliophysics Digital Resource Library, as well as the NASA Center for Helioanalytics, and connecting those efforts to NASA's Grand Open Science Initiative, or Transformation Open Science. The Heliophysics KNOWledge Network represents a kind of convergence of ideas and methods to respond to these challenges, becoming an exploration of the dimensions that are needed for a knowledge commons. So a few of the dimensions that we're exploring are detailed here, and I won't go into detail into all of the efforts that are being led in each of these dimensions, but I will point you to the resources where you can learn more. Included in this is a review, understanding first, what are the knowledge systems that have been developed within heliophysics? We've done some outstanding work within this community. Many of the people in the audience will be a part of those efforts. And the review intends to bring together that knowledge so that we can build upon it and interconnect to it, rather than reinventing or certainly not replacing them, but benefiting from and feeding back to those. The second effort is to understand what semantic resources, which I'll speak about in a moment, are out there, and try to understand how we harmonize across those. This is a very challenging but vital process for the future of our infrastructure. And then we start to build higher level semantic tools, such as ontologies that map the concepts and relationships in our community and in our data and in our knowledge to one another, so that we can build things like knowledge graphs, where we can provide interactive platforms for interacting with those, better search and discovery and integration tools. And then finally, the ultimate goal of all of this is science. So bring these things together in service of frontier scientific discovery. So we're doing these across a number of dimensions within Helio-KNOW. All of these developments I'll mention are being done entirely openly, and we invite everyone to contribute to them. A central component of what Heliophysics KNOWledge Network is the workshops that we lead. These are focused 90-minute working periods around important items within these categories, and I welcome everyone to be involved in those. I would like to describe only a few of our ongoing efforts, specifically in creating semantic technologies that can benefit heliophysics infrastructure. But first, a few quick definitions. So I've spoken about semantic technologies, but I just want to explicitly state that these are tools that encode semantics, or the way that we describe meaning with meaning in language, what's in our data, alongside data so that they can be human and machine readable and interoperable. An ontology is very simply a system of concepts. It's a schema that describes the concepts and, importantly, their relationships in a graph form. From an ontology, you can instantiate a knowledge graph by bringing information and bringing facts to those data schema, and that allows those to be explored and navigated between the relationships themselves. And then finally, a knowledge network is an interconnection of different knowledge graphs. So if a knowledge graph represents a single domain, a knowledge network would be an interconnection between those domains. We're trying to build to these knowledge networks with Heliophysics KNOWledge Network. I would like to describe some of our efforts and talk about them in the context of this idea of semantics. So semantics are basically representing the meaning in our data and information. And these take many different forms. And I really like the visual put together by Ruth Dewar that lays it out across a continuum from weak to strong semantics. And I'm going to talk about our efforts in the context of this picture by showing you how we're building up across this semantic spectrum. So first, at the lower end of this are thesauri and glossaries. One project that we've been leading for the past 8 months is to enrich the representation of our fields domain within the NASA Astrophysics data system, a very important search and discovery tool. So NASA ADS is now covered to support heliophysics and planetary science, in addition to astrophysics, and earth science will follow. So our goal has been to create a set of concepts and their semantic representation that extends the coverage of heliophysics literature by NASA ADS, and to provide that extension in a manner interoperable with the semantic resource that is used by ADS called the Unified Astronomy Thesaurus. Things that we've achieved in this project are to improve heliophysics representation across 14 queries that were designed to cover the breadth of heliophysics phenomena and science. We designed a path for all fields to improve their representation within ADS, and also kind of general guidelines for improving search and discovery tools for a domain. We created a quantitative and qualitative evaluation framework to determine changes and improvement in an infrastructure's search and discovery capabilities. We produced a heliophysics glossary that harmonizes across numerous existing and disparate helioglossaries. And we seeded community involvement, participation, and cohesion to develop these semantic tools needed. We, through this project, and as an extension incorporating the NASA Center for Helioanalytics, held the first Heliophysics Vocabulary Camp workshop. In creating this infrastructure, we noted that it was vital to work with the community, allowing them to guide the design choices. So we designed this new form of interaction called the Vocabulary Camp that builds on well-established methods from the semantic technology community as a place where domain and knowledge scientists can co-create the changes that we will implement in our infrastructure. You can learn more about it from the QR code in the slide. One of the important outcomes from our first Heliophysics Vocabulary Camp was to create a complete heliophysics region-based taxonomy. This taxonomy is shown here, which you're not expected to be able to read. Happy to provide a link to this where you can interact with it both programmatically and as a visual. But these will be included in the next update to the Unified Astronomy Thesaurus to take place in December 2022, so that publishers and authors can use it to label their research artifacts, and it can be used by search systems and faceted search. But the goal of our efforts with Helio-KNOW is to create the most sophisticated semantic resources, those that support the kind of discovery and integration that complexity sciences and our wicked problems require. And so we're developing a number of different ontologies or data schema that can be useful in designing our infrastructure. And so heliophysics has a number of different phenomena that we need to capture from these ontologies. So we're doing this in a number of different ways, and we're borrowing the concept of modular ontological development that is growing in popularity within the within the semantic technology community. The first effort was to create a modular ontology for the geomagnetically induced current phenomena. We have been working on this, and we've created a full ontology. You can grab the link in the paper there, and then also instantiated that with data from the solar wind information from geomagnetic activity indices, ground-based magnetometers, and GIC monitors from power grid utilities themselves. And we were able to bring all these data together through this ontological system into a knowledge graph that can actually be interacted with and navigated by someone like a power grid engineer who needs to know the contextual information for their GIC observations. And so the video in the slide is just showing a very brief demo of what can be done with that ontology. We're now expanding this into other domains as well and trying to represent other heliophysics phenomena. The conceptual model that you're seeing on the slide here is one that we've been developing for magnetosphere-ionosphere coupling as a phenomena. And so it captures things like particle precipitation, electric field enhancements and changes in conductivity in the ionosphere. And so this is another modular ontology that can then be brought together with some of the other patterns that we're developing as well. But it is not just about the physical phenomena that we need to map. We also must understand how to interconnect our research tools themselves. So we've held workshops with the heliophysics community to define these interconnections. So what you're seeing here is a conceptual model that relates heliophysics analysis tools, different pieces of software, different documentation, different individuals' representation and development of those software, and relates those via their relationships and allows them to be navigated, which is an important modular piece of heliophysics knowledge. Finally, we also must understand how to connect the community themselves, tools to find and collaborate with one another. In partnership with the Center for Helioanalytics Knowledge Team, we've been developing an ontology that allows a community to be represented and better find and collaborate with one another. The result has been the Community Action and Understanding via Semantic Enrichment, or CAUSE ontology. And that ontology represents important topics and concepts within the research community, individuals, groups, organizations, skills, and expertise. We've used the NASA Center for Helioanalytics to instantiate this ontology with community data and have created a complete knowledge graph and an interactive platform to explore that so that our community can know who's a part of the center, what research they've been doing, and better interact and know how to engage with one another. We call this the cultural social nucleus of an open community, a multi-level community knowledge graph and its application within NASA. This talk kind of builds towards this concept of a knowledge commons. We call a knowledge commons a combination of intelligent information representation, and the openness, governance, and trust required to create a participatory ecosystem whereby the whole community maintains and evolves this shared information space. We believe that a knowledge commons is a core technology defined to include both the hardware and software and cultural technologies of a solution for a more inclusive, open, and equitable society, one where everyone is responsible for co-creating that evolution of the collaboration space. So a knowledge commons includes technical knowledge representation systems, which I've been pointing to in this talk, and also a social community system for producing and governing the knowledge network. We believe that the path towards creating this commons lies in an embrace of radical collaboration, new scales of interaction, and the corresponding changes in thinking, in community structure, and in support that must accompany this movement. So the knowledge commons can be a framework for how we improve our infrastructure. I want to conclude this with one perspective on some of the pitfalls or traps our infrastructure improvement efforts fall into, and how the knowledge commons framework might help improve those. So the first pitfall I want to talk about is the fact that we continually have our efforts result in remaking silos. I think we recognize this pitfall commonly. There's a couple of solutions that the knowledge commons framework suggests. First is create processes where the data use changes the structure and access mechanism. So create a living archive rather than some static entity. Second, to consider graph or network structures, these ontologies that I was presenting, and make relationships first-class citizens so that they can be navigated. So part of this is that our efforts to improve our infrastructure are often too insular. And we need to understand the landscape that exists across disciplines that are doing this work and invite them into our conversations, design, and research. The second pitfall is that users are often poorly represented in the designs of our data systems. And we can solve this by adopting a participatory design practice and hold them regularly and support them. Our best designs are often underutilized because of this very reason, and we need to better meet researchers where they are. So we need to work on the platforms and their interactivity. And finally, we need to think of infrastructure as only we often tend to think of infrastructure as only representing our observational and model data and seldom as community data. What this means is that lost on our infrastructure is a means to think about the community interaction and behavior. We can solve this by relating researchers to one another beyond mere citation networks, for instance, incorporating more elements of a researcher in a group of research and how we can connect to one another. The cause ontology is an effort to do this. I will conclude with an emphasis that the knowledge commons provides a framework for overcoming these pitfalls and thinking about more capable and evolvable systems. So I'll conclude with this reiteration that the commons is an important idea for conceptualizing many of the problems we face with data, information, and digital spaces today. And in some ways, the challenge of our generation is to keep the pathways to discovery of future knowledge open. I hope that the commons will provoke thought and discussion and rich discussion and conversation around how we can use that to improve our heliophysics infrastructure. Thank you.